I'm going to finish chapter 18 and get a good start on chapter 19. This way I'll be able to finish chapter 19 next Monday. And you've got an exam coming up for that on May the 3rd. All right, and that would be chapters 18 and 19, and that's the remainder of the course. All right, so let's get started on, or let's finish chapter 18. All right, what we did last time was we talked about calculating a KSP using delta G, and we looked at this. And we determined the KSP. It was slightly different than what we got in the tables, but it was pretty close. And again, there's this relationship that you have to understand between equilibrium constants and this state function, Gibbs free energy. Right? I mentioned that back in chapter 15, but now you actually know what the relationship is. And again, what you want to remember, because so many people forget, is that if you're calculating, or if you're determining rather, if a chemical reaction is spontaneous or not, don't look at delta S. You're looking at delta G. Because delta S only talks about the change in internal entropy, which is not the complete picture for spontaneity. All right, again, don't make that mistake. Too many people do. Why do they? They don't practice. Oh, and there's one other thing I should mention as well. I posted a couple of practice assignments, one for buffers and one for titration curves. It was kind of alarming to me to see how few of you had actually looked at that before this morning. All right, that's not the intent of these things. There are a couple of you who deserve some extra or some credit for this, because some of you did it a number of times. And really, I think that's the best way to do this, is you go in there and you practice over and over and over again. All right, and some of you got rewarded a little bit for that, because I was able to go back in and look at some of the responses and grade them. All right, when I post assignments like that, don't wait till the last minute. That's not going to do you any good. You're not going to get any benefit from an assignment if you do it like that. It's just like Alex. If you wait till Saturday night or Sunday night to do Alex, you're not going to gain what you need to from it. You need to be doing it consistently. And you need to think about that with respect to your studies for your final as well. If you wait until Tuesday, May the 9th to study for this final, you're not going to pass it. It's pure and simple. Okay, you've got to start preparing for it fairly soon, probably even before the 5th exam. All right, so let's look at calculating an equilibrium constant for a different reaction. And in this particular case, what we're going to do is we're going to calculate the equilibrium constant for the combustion of methane at standard conditions. And of course, what that really means is that all the gases involved in this reaction are at 1 atmosphere, because the pressure is constant. And again, if we're using the values that come from a textbook or some other source, we're also going to determine this at 25 degrees Celsius or 298 Kelvin. And of course, that has relevance when we start talking about equilibrium constants, because that's the temperature we're going to use. So the first thing we want to think about is, what's the reaction we're looking at? The combustion of methane, or the complete combustion of methane. It's this reaction. We start with CH4 gas. We combine it with oxygen. And our products are carbon dioxide and water. All right, now what state is water going to be in? That does matter here. Let's put it in the gas state. Okay, so that all the components of this reaction are in the gas phase. Is this balanced? Sorry? What do you say? Okay, yeah, we're going to do a 2 in front of H2O. What else? Anything else? Yeah, what are we going to do there? A 2. All right, so here's something to remember too. All right, we're balancing with whole number coefficients. So what does this represent? If we balance in this fashion, we're talking about the combustion of 1 mole of methane. Okay, we could also say, well, what if we wanted to put this reaction in the perspective of oxygen and say, what is it per mole of oxygen? Then we would have the coefficients. Okay, now that's going to have an effect on the delta G zero that we calculate, and it's also going to have an effect on the value of the equilibrium constant, as we learned before. Okay, because if delta G is half of what it would be if we have these coefficients, then the K that we calculate would be the square root of what we would get if we left the coefficients as they are here. Okay, that's something to keep in mind. All right, it's kind of hard to track. So really what you could say here is what we're doing is we're calculating the heat of, the Gibbs free energy for the combustion of 1 mole of methane. Okay, so let's go ahead and do that. We're going to use tabulated values. So we're going to calculate a delta G zero for this reaction because the tabulated values, represent standard Gibbs free energy of formation values. All right, in our products, what do we have? We have 1 mole of carbon dioxide gas. And again, you've got to be careful because not so much for CO2, but for water, you have to make sure you look up the right standard Gibbs free energy of formation value for H2O gas. All right, and then in our reactants, what do we have? We have 1 mole of methane and we have 2 moles of elemental oxygen. Now let's start with this one. What's the standard Gibbs free energy of formation value for an element such as oxygen? Yes, 0 kilojoules per mole. All right, you're not sure about that, you can always look it up. But yeah, again, that's the definition. That's the frame of reference that we use for standard Gibbs free energy of formation values, is that any element in its elemental form has a standard Gibbs free energy of formation value, just like a standard enthalpy of formation value of 0 kilojoules per mole. All right, what is it for water? Because that's probably close to oxygen. What do we find? Sounds good. Negative 228.6 kilojoules per mole. All right. Save that too for the next problem because we'll use it again there. Okay, what about CO2? That's probably under carbon, and I would bet CH4 is under organic compounds. Although it might be under carbon as well, depending on which table you're looking at. Negative 394.4 kilojoules per mole, okay? And for CH4. Okay, thank you. Negative 50.75 kilojoules per mole. All right, so if we add all this together, what do we get? for a total delta G of this reaction. Yep. Oh, yes, thank you. Here, you mean, yeah, on the equation. Okay. All right. What do we get? That sounds not negative enough. Let's see, negative 394.4 plus 2 times negative 228. I get negative 800.9 kilojoules per this. Okay, so what does this tell us? Two things we want to think about. First one is this reaction spontaneous or not based on the delta G value? Delta G is negative. What do we conclude about the spontaneity of this reaction at the conditions we've calculated delta G? It is spontaneous, yes. Okay. All right. Now let's think about one other thing as well. If we're going to calculate the equilibrium constant for this reaction, we're going to use this equation. The delta G0 for this reaction is equal to negative R times T times the natural log of K. All right, so what this implies is that if delta G is negative, then the natural log of the equilibrium constant has to be positive. There's that sign change. All right, so again, you can draw that conclusion as well. If you have an equilibrium constant whose logarithm is positive, which means that the equilibrium constant is greater than 1, that tells you that the forward reaction that you're looking at is spontaneous. All right, so you can tie all these things together. You could say for the previous example, if you were looking at it, well, if I look at the K value for the previous example, we got a K value of something times 10 to the negative 13th. That's a really small K value. It's less than 1. That means that delta G for reaction is positive, and therefore the forward reaction under standard conditions is not spontaneous. All right, in this case, we see the reverse. Delta G is negative. That implies that our K value is going to be greater than 1. Okay, both things can tell you the same thing because they're tied together. So if you tell me on an exam, oh, I calculated the equilibrium constant for this reaction and it's greater than 1, that means the forward reaction is spontaneous. That's a reasonable conclusion because of this relationship. All right. So in this particular case, we're going to rearrange it and we're going to solve for the equilibrium constant like this. Now again, what we have to pay attention to, and this is one of the more common mistakes that students make, is that if we're going to use this equation, the thing that we have to do also is to change our delta G value into joules, which of course means we're going to multiply it by 1,000. So if we multiply negative 800.9 kilojoules, we get negative 8.009 times 10 to the 5th joules. Or if you prefer to write it as negative 800,900, that's fine too. All right, it's going to work the same way either way. And of course, I forgot the negative sign down here. So in this particular case, if that's true, the natural log of my equilibrium constant is going to be negative 8.009 times 10 to the 5th divided by R, which is, again, we're going to use 8.314, and divided again by temperature, which would be 298 kelvins. So what do we get for a natural log of K? Okay? Yeah, 323. All right. So, how can we get an equilibrium constant from this? We can say that the equilibrium constant is equal to E raised to the 323 power. What happens when you try to do that in your calculator? Does anybody have a calculator that can... Yeah, you get an error. Okay. Why do you get an error? Any ideas? Would you consider this to be a very large number or a very small number? Yeah, it's going to be huge. All right. Most scientific calculators, especially these cheap ones that I recommend, don't handle numbers that are larger than 10 to the 100th or less than 10 to the negative 100th. All right, so here's what we have to think about. What's the relationship between natural log and log? All right, so we can circumvent this problem. All right, we do know that this is very large. I like to put it in terms of 10 just because it gives me the ability to compare it with other equilibrium constants that we've looked at before written in scientific notation. All right, here's what we can say. To get the number 10, that's equal to E raised to the 2.303 power. Okay? And so what that means then is that the natural log of the number 10 is 2.303. All right? Or another way of putting this, and this is what's useful here, is that the log of a certain number, say x, is equal to 2. Excuse me. No, I've got this backwards. Sorry about that. The log of x times 2.303 is equal to the natural log of that same number. So in other words, the natural log number is 2.303 times as large as the base 10 number. So what we could do is we could say, all right, in terms of our k, we could take 10 and raise it to this 323 divided by 2.303 power. All right, now I'm not going to try raising 10 to that because I already know my calculator can't do that. But I can divide 323 by 2.303. Yeah, 140. All right, so why did I do this? I wanted to illustrate this one point, okay, where if you have a really, really large K or a really, really small K in this kind of calculation, which is possible, all right, then you can use this relationship to bring the number into a usable number in base 10 units just by messing with the exponent. All right, that's one thing. There's another thing here. And let's go back to chapter 15. There was a very brief mention made in the book. I actually didn't make it in class. But basically what your textbook says, and is quite reasonable, is if you have an equilibrium constant, such as this one, that's greater than 10 to the 50th, then for all intents and purposes, what you can say is that this really isn't an equilibrium, even though we write it as such and we treat it as such. But given the magnitude of this, 10 to the 140th power, basically what it's telling us is that when this system reaches dynamic equilibrium, if it ever does, then there's nothing left in the reactants. Because if you do the math, you're going to get fractions of molecules of reactants, small fractions of molecules. It doesn't happen. Okay, so that's what you can think about. So, I mean, basically, even though we've done this calculation and it is theoretically possible to do this, basically what it's telling us is, okay, this reaction has such a negative delta G that it's just going to go to products. All right, which goes back to what we talked about at the very beginning of chemistry, where we look at chemical reactions in that way. We don't look at them as being dynamic equilibria. All right, there are reactions like this one that can just form entirely products. You're not going to detect any reactants when all is said and done. Okay, now there's one other thing I want to point out here, which we talked about before. Not only from delta G do we get whether a reaction is spontaneous or not. Okay, that's a qualitative assessment of delta G. But the actual number that we calculate represents the maximum amount of work that we can get from a chemical reaction. All right, so really, if we were to engineer this reaction in the proper way, we could get a lot more work out of it than we do if we just burn methane. All right, now sometimes by burning methane, we get a desirable result. We get heat. Okay, a lot of us use natural gas to heat our homes, and this is the reaction we do to heat our homes. All right, so we're producing a lot of heat, but we could also engineer this reaction to maximize the amount of work. And this is something I want you to think about because it's a really nice lead into the next chapter. All right. How can we maximize the amount of work that we get out of chemical reactions? All right. We actually have the technology to do this. We just need to start using it more. That's what we need to think about. And this is, I think, one of the underlying themes of the last chapter of this course. All right. Let's do one other thing first, though. What we want to do next is we want to determine the boiling point of water in the similar fashion to what we did with the decomposition of calcium carbonate. All right, now this is probably going to give us a more accurate result because the boiling point of water is actually closer to room temperature than the decomposition temperature of calcium carbonate. All right, so here's what we're looking at. If I'm looking at a boiling point, essentially what I'm doing is I'm looking at a reaction where I'm taking a substance in the liquid phase, or the liquid state, and I'm changing it to a gas. Okay, now here's what we can think about. If I'm at a boiling point, what I can say is that the delta G for this reaction, notice how I didn't write delta G 0, is 0, okay? Because this reaction at the boiling point is at equilibrium. All right, if something's at equilibrium, then delta G for that reaction is 0. All right, that's something we defined earlier. All right, so here's the question. How could I calculate the temperature at which this is going to happen? All right, let's go back and remember the Gibbs-Helmholtz equation. One of the ways we learned how to calculate delta G is if we have the delta H and the delta S for a reaction. That's the Gibbs-Helmholtz equation. All right, again, that's one of the one of the 3 ways we've already learned about calculating delta G. And again, when we get into the next chapter, we'll get to the 4th way. So delta J is equal to delta H minus T delta S. Now, if we take that and we say, okay, if delta G is 0, then we have this. Oh, crud, it's not plus, it's minus. Sorry about that. So it's minus T delta S. And of course, if we rearrange this equation, then the temperature at which the spontaneity of a reaction will change is going to be delta H divided by delta S. All right. Now, the other thing we have to keep in mind, though, is that that means that delta H and delta S must have the same sign. They either both must be positive or they both must be negative. All right. Let's look at this reaction. What would we predict for a vaporization? Is the change in internal entropy going to increase or decrease if we start as a liquid and we end up with a gas? It's going to increase, yes. Okay, now let's think back even further. Because we talked about this I know we talked about this the very first day of class. And that is, when I vaporize something, is delta H positive or negative? In other words, do I have to pump heat into these molecules to separate them, or is heat given off when I separate molecules? What did we say back in chapter 11? It's, well, okay, okay, be careful about what you're saying. I think you're on the right idea, but you got the wrong sign. Yeah, you've got to pump energy into this. So from the perspective of the molecules, what you would say is, okay, delta H is positive. Okay, so we know just by our qualitative assessment of things that both delta H and delta S are going to be positive for this reaction. All right, so the next thing we're going to do then is we're going to calculate each one using tabulated values. All right, so we're going to use standard enthalpy of formation values to calculate delta H for this reaction. Okay. And in our products, we have 1 mole of H2O gas. Times whatever the standard enthalpy of formation is for water gas. And in our reactants, we have 1 mole of H2O liquid. So what do we get for standard enthalpy of formation values? And again, you want to look at the first column. All right, and you're also going to want to keep that open because when we calculate delta S, we're going to be looking in exactly the same place, except either the second or third column, depending on which table you're looking at. What is the standard enthalpy of formation value for H2O gas? Okay. Negative 241.8 kilojoules per mole. All right, and what is it for H2O liquid? Okay. Negative 285.8 kilojoules per mole. And so if we take the difference between those two, what do we get for a delta H for this reaction? 44 kilojoules. Okay. All right. What have we just done? We've just calculated the heat of vaporization of water. All right, because what we've done is we've calculated the delta H for the vaporization of 1 mole of H2O liquid. All right, let's do the same now with delta S. So let's calculate delta S for this reaction at standard conditions, 25 degrees Celsius. Products, we have H2O gas, and in our reactants we have H2O liquid. So what are the S0 values for both of those? Same part of the table. Okay. Oops. 188.7, that's joules per mole Kelvin. I'm sorry, for H2O liquid, what did you say it was again? 69.91. And that's joules per mole Kelvin. All right. And so what do we get for delta S? Sorry? What was it? Okay. We'll do 118.8. What's the, what are the units? Yeah, joules per Kelvin. All right. Again, we've got to pay attention to that because if we combine these two numbers together using this equation up here at the top, then either we have to change the delta H into joules or we have to change the delta S into kilojoules per Kelvin. We can't just divide one by the other here because we won't get the right answer if we do. So which are we going to do? 6 of one, half dozen of another, right? Okay. Yeah, so we could change delta S to 0.1188 kilojoules per Kelvin. All right, that works. So now we can say, all right, let's estimate the boiling point of water. We're going to take that delta H, which is 44 kilojoules. It's actually 44.0 kilojoules. And we're going to divide that by 0.1188 kilojoules per Kelvin. And so that means the units of our temperature will be in kelvins. That's fine. Okay, so it's going to round to the nearest Kelvin of 370. All right, so we're off by a little bit, but not very much. All right, and this goes back to what I was saying last time. When we do these kinds of estimations, they work the best if we estimate close to 25 degrees Celsius. Okay, the closer we get, the more accurate it is. All right, one of the things you'll notice is on the worksheets, there are several different liquids that you can look at for this chapter. All right, I'll post those after Wednesday. You can start looking at those. And I deliberately chose liquids that have low boiling points. So the estimations are actually even more accurate than this one is. Okay, but you can do this kind of thing. All right, you can estimate, as we've talked about before, if you have a reaction where the delta H and the delta S both have the same sign, you can estimate the temperature at which the spontaneity of that reaction changes. All right, probably you're more likely to do something like this, where you're estimating a boiling point. All right, and again, there's some practice problems you can do on the worksheet that will do that. I would strongly recommend you spend some time working on those. All right, so that pretty much finishes what I need to say about chapter 18.